Okay, we're on.
Hi, everyone, and welcome to the 9th episode of Machine Learning at HZG, titled The Best of All Possible Worlds. Today, we're going to talk about how to tune climate models. This is a really difficult task.
Okay, we're on.
Climate models are these big pieces of sophisticated mathematical and computational machinery. Their equations are not simple. Their code bases are even less simple. They're written in Fortran. They run on very complicated, specialized hardware. And we want to not only run them, we want to figure out which of their free parameters should be tuned in which way to get a good match to observational data. This is a really, really challenging task. Almost seems impossible. So what we're going to do today is just go over a few of the existing approaches of how to approach this really difficult task. Marcel's going to start off covering, if I'm pronouncing this right, Hourdin or Hourdin, a review of the art and science of climate model tuning, just describing what the problem is and what are the major considerations. And then I'm going to take us through a few papers that attempt this really challenging task. I'm going to talk a little basically about how they approach the problem, what tools they use, what data they use, which models they use, what they can and cannot tell us. I'm going to skip over most of the specific scientific conclusions and a great many technical details to really try to get a conceptual understanding of what these approaches are and what are the tools we have in our toolbox in trying to fit these monstrously complex models to data. So with that, I'm going to turn over to you, Marcel, and you can go over the Hourdin review.
Okay, hello everyone. Can everybody hear me?
Yep.
Great. So as David said, I'm gonna start with the review, which is written a bit like an open letter to the climate modeling community. The title is The Art and Science of Climate Model Tuning. Just as this very little abstract here emphasizes, they made a survey for the rational and diversity of approaches for parameter tuning climate models. And a lot of the text is really about arguing for better documentation and more transparency of what people do with their parameterizations. Since we're going to talk today mostly about what methods there are for parameter tuning and what you can do, we're going to skip some of the discussion, but for everybody who's interested, I really recommend also going more into the more discussion parts of this paper, I would say, where they're trying to argue for better documentation, for more exchange, and also for questions what constitutes good targets for parameter tuning, which will, as I understand it, not be the main focus for today. But with this, let's dive into the paper. So the background here is that the authors here have also been involved in the CMIT project, the Climate Model Intercomparison project. At the time of the paper coming out in 2015, it was the 5th phase. And as you can see here, highlighted, the authors argued that even though parameter tuning is part of most or every of the involved model contributions to the project, there was actually no requirement for also documenting this. So this was kind of the background where the authors started from. To then talk further about what parameter tuning in climate model actually entails. Interesting enough, to define model tuning, they go back to a definition from statistics, from Fisher in 1922, that says usually this happens in 3 steps. So first of all, you define a model, in this case very complicated climate model. You would then estimate 3 parameters that you don't know, and in the third step, you might then estimate the uncertainty over these parameters that you don't know. They argue that this definition from statistics can also be applied to climate modeling, and climate models themselves, as we see here, they are founded on large parts on well understood physics, but there's also a number of heuristic process representations involved. So these are then often called parametrizations. They deal with processes that are not resolved within the model, and within these parametrizations, with these parametrizations usually come a bunch of free parameters whose numerical values are poorly constrained by first principles or by observations, in which it does have to be set or tuned. So within the context of climate modeling, these parameters of these parametrizations are then the target of parameter tuning. There are some other arguments, like that already the grid resolution of the model could be considered some parameter to be thought of as really being tuned in order to resolve certain phenomena that people are interested in. But for the purpose of this particular study, and I think for the rest of today, we're mostly going to be talking about parameters of some parametrizations. They then go on and explain a bit about the stages where parameter tuning happens. First of all, there appears to be an initial parameter tuning phase when people first set up their models, often on a locally restricted version model runs, for instance, single column versions of a climate model. Then when different components are brought together, there needs to be an alignment phase where free parameters of the different components then are again adjusted so that different components work better in union. And then once the full system is assembled, there can be some final tuning. Now, just as a quick overview, they have this one paper, this one figure actually reproduced from another paper, Hourdin et al. 2012, for the ACAM model, the atmosphere part here, where they just have a very quick sketch, and I don't want to go too much into the details here. It's just that, so these are different parts of atmosphere systems, of the atmosphere system, and they have these little letters in here that indicate certain parameters that need to be tuned. Here's a list of them: convective cloud mass flux about the level of non-buoyancy, for instance, is one of these parameters. Or for instance, the deep convective cloud lateral and entrainment rate. You see, the main point of this figure is just to show that even for a small part of the model, you have up to letter G, so there's a number of these parameters to be set. Why do these parameter settings actually really matter? Is explained in this part. So for different climate models, there might be a variety of goals that people want to achieve, depending on the exact target of the model and the exact project that investigates a certain aspect of climate. But one thing that is often shared by most of these models is that you want to achieve a energy balance regarding the total amount of energy that enters the planet and that leaves the planet. The total system is roughly in equilibrium. There's some current heat uptake as there's an increase in the mean global temperature, but there's roughly a balance, and not getting the balance exact can have, for instance, really profound differences in global mean surface temperature, for instance. So you can set these parameters, and you have to set these parameters in order to get get the system to behave sensibly in a global meaning, which I think is quite nicely described in this figure here. So here you have the ice fall velocity parameter, so the velocity with which ice crystals fall on this axis, and you have the radiation in watts per square meter on the other axis, and you have in different colors, you have a number of different models that all share this one particular parameter. You have a target region here indicated in gray. It's not exactly known the exact value that you want to achieve, but there's a region of plausibility that you're targeting for. And the first thing to notice is that in order to be within the plausible or the desired target region with respect of the radiation of the model, different models actually need to set this parameter to different values. So if you look at the IPSL CM5B model, you want to have a fall velocity parameter above 1 to be in the target zone, while for the IPSL CM5A model, you actually need around 0.5. And the other thing to really see is, of course, that for most of these models, for instance, if we stay with the CM5A one, being outside good regions for the fall velocity parameter means that we're getting very far outside of the sensible radiation region that we want to obtain with the model. So there are these parameters in the different parameterization parts, and we really want to set them to sensible values in order to get simulations that match certain observations, or at least regions of observations that we want to achieve. David will later talk on much more detail about which different methods we may apply here. But just very quickly, one thing that the authors here present is that what one should do in terms of reproducibility and transparency is use objective methods to tuning these parameters. That does not work by hand and purely out of personal expertise of the involved people, but that one could, for instance, write down an objective function and then numerically optimize this. They say that, broadly speaking, there's two ways of doing parameter tuning, which we will later also see. One is just an optimization where the target is a single optimal value for a parameter, for instance, as we've seen before here, the ice fall velocity parameter, which for these different models, here you see this square and the diamonds. These are the eventual parameters that were used for this in the CMIT5 runs. So there is a parameter optimization where the target is a single parameter value, and then there's in a second class of methods, which they here call a Bayesian approach. It's also called uncertainty quantification. The second class of methods is going for a range of possible parameters that are consistent with, say, functional behaviors or realistic behaviors of the climate model overall. So these methods may, for instance, represent remaining parameter uncertainty with a distribution over possible parameters, instead of just a single value, which then also reflects that we don't know exactly which value works, and that there might not be a single one. There are challenges, which we will then also see much more in detail once we go to the individual papers. For instance, if you tune your parameter by trying to optimize some optimization metric that you've chosen to, for instance, get your energy balance correct, this might actually mean that you're introducing bad model behavior somewhere else where you're currently not optuning for. This is something we will need to keep in mind. And then just as a final remark, a class of uncertainty quantification methods that explicitly avoids problems of over-tuning is called history matching. And the Williamson 2015 paper we will then see later. Yes, so this is another quick example maybe that we can quickly look at. A more applied example. So if I zoom in a little, like this. So in this figure here you see 2-meter temperature anomalies in the CM3 model, which went into the CMIP5. On the black line you see observation data for the anomalies, the global anomalies from the year 1850 to slightly beyond 2000. And in green you see a model run that was taken from CMIP5. And what they did here in this case after the run was that they went back to parameter tuning, and they specifically tried to tune for the orange line. They specifically tried to tune parameters of the parameterization to actually match that temperature curve on hindsight on. So they ran the model with the parameters that they tuned the way they had originally. That was green, and then after the fact, after some criticism, they looked back and they checked out if they could have gotten closer. And then in another parameter setting, more to the extreme other side that we see here in blue, you actually see that this can also become much further away from the observations. So setting these parameters can really make a big difference. Then just to very quickly conclude, so one thing that I said I'm gonna quickly skip about in this paper is that the authors really called for better documentation of what different methods of tuning people use. And since this was in 2015, I just very quickly wanted to show how in the CMIP6, the next generation, this actually kind of showed, and the authors actually were heard. So if we look at the CMIP6 CIS model under comparison project, so this is one of the CMIP6 projects, and we go into Appendix B, we can now see that there is, in this part here, that they are now specifically asking for the tunings to be reported as well. So this is something that is picking up and that is getting more attention, as we will see. So this would be it just for this introductory discussion paper. If anybody has any questions, just raise them. So I can't see the chat right now as I'm sharing the screen.
I'm keeping an eye on. I don't think anyone's raising their hand. Zoom has recently changed things around, so if you want to raise your hand, you have to go to the participants list. In the bottom right, there's 3 dots. You click on that, and then you can raise your hand. Or you can just write in the chat, and I will keep an eye on that as well. And I will quickly check the YouTube as well. So yeah, this is a good point. If anyone has questions, if anyone has comments as well, or opinions about climate model tuning, if anyone has experience, we would very, very much like to hear about it. Okay, but then otherwise, let's move on. Let me open up the YouTube chat before doing so. and then we will get to the first of these methods papers. Okay. So I think we're going to start off with an optimization approach first. Oh, is there someone with their hand up? Let me just see.
Yeah, that was me, actually. Yeah. Here's Chris, sorry. It's great that you showed already kind of an answer in a way that the community kind of responded in a way that in the CI's model comparison projects, they're kind of are open to these questions. But I mean, the CS models are a little bit younger, the whole community is a little bit more open, and this is not so historically grown like the atmospheric models or the ocean models. Do you know any response to of the modeling communities? So like, were there a big discussion around that? Because I can imagine that the answer would be like, yeah, we want to, but it's hard, or something like that.
Let me just quickly, I did pick out this one project in particular because they had written it out so nicely. If I may quickly grab again the screen for just a second. So if you see my screen right now, so this is the formal documentation for all CMIP projects. And if I quickly search in here, for tuning, which used to be a word in this text. I don't know why this doesn't work anymore right now. The model, it was called the model, just one sec. Here, in all of the different projects of CMIP 6, they do require that tuning is now better documented. So this is for all of CMIP 6. I showed only CIs because in that paper it was best described, I think, and here it's a bit short.
They just asked about the kind of the scientific tuning properties, so not in a way that they actually could like take the model, change everything, and have a good documentation around it. It was more like even the scientific around it would be helpful.
Yeah.
Yeah. Okay. That's interesting. Yeah, I haven't seen this paper before, so that's kind of really interesting to see. I'm not sure if this is really helping the other communities, but I guess we see some papers now. So sorry for interruption, but I think this is really interesting. That, I mean, you try to change the community from the inside, and sometimes it's good that it comes from the outside. So and this sounds like a good opportunity. Yeah. Okay, I mean, thanks. Yeah.
Chris, I think it's quite an interesting question. So something I was going to touch on later too, though I think it's worth bringing up now, is, and if you look at the papers where, I tried to choose some papers which cover different approaches to climate model tuning, and it's quite a big field, and we couldn't cover everything, and you could learn a lot just by reading the papers that are cited in what we'll cover today, or the papers that have cited them, if you want to look them up on Google Scholar. But one thing that struck me is there's relatively few models that show up in the tuning. The Hadley Center models are really big in this literature, and these guys are interested in it. But I guess, as we're also discovering sometimes, it's not so easy just to get someone's model and to run it. So if the people who have access and control are interested, then I think the tuning will be discussed and there'll be papers on it. And if not, then yeah, maybe not. I think the other thing is, a lot of the tuning studies we're going to cover today used these perturbed physics ensembles, which we'll cover in a second, where they did all these model runs with different parameters using distributed computing on people's home computers. They volunteered to this climateprediction.net, weather at home, and I'd be very curious if this data is actually available. I know I would love to get my hands on it. So availability of data and the ability to run models, I think, are big questions in what you might call the democratization of climate model tuning.
Yeah, and then on top you have kind of the sensitivity of these models on different machines. So I'm pretty sure you can't. The term reproducibility is not possible to some certain extent, right? Because you tune on parameterizations, which are really kind of the small scale stuff in a model. Yeah, I can really imagine that these climate communities say, yeah, it's important, we know that, but it's really hard to kind of, yeah, but you're right. It starts with giving data out, right? I mean, it could be easy like that, right? But I think if you want to make it real case studies with models and changing tuning parameters without messing up the model, there's a lot of knowledge you have to get and around the model system and besides all the physics to make these experiments next to maybe the official CMIP ones or something like that.
I think there may be a bigger question of reproducibility beyond just tuning then. Can you reproduce someone else's results running the same code in the same experiments? And I think in some cases you can, especially in the simpler models. But it's a big open question. And I'm sure that probably some of the other people in this seminar have more experience there or have more expert opinions, but it's not a simple question.
Okay, thanks, guys.
All right, so I don't see any more questions right now, so let me just jump into the first of these papers. I'm going to move really quickly. So I encourage everyone to interrupt me frequently with questions, with comments. But I'm just going to try to cover these core concepts and keep moving, essentially. All right, so we're going to start with Tett et al. 2013. And they do something very nice and very simple. And I think it's great to use a simple approach, not trivial, but simple, to introduce a lot of these concepts. So what they have is a climate model. They've chosen several parameters to tune. They've chosen to use the HZG model. It came out around 2000. It's pretty notable in that it was one of the first climate models that didn't require a flux adjustment for radiation, right? So you could run it with some parameters and you would actually get the right answer without having to kind of fudge the energy balance like a lot of earlier climate models. So they did that. They used this particular model, and it has a bunch of these knobs to tune, a bunch of these parameters. Here, I'm just going to pull up some of these initial maps where they show when they came up with this model, they were able to get the mean temperatures right and so on without doing this flux adjustment. So, okay, they're using this model, there are parameters that they can tune, and they're trying to tune them in order to match some observations. And these are basic things like, the land temperature, precipitation. We'll cover what they were in this particular paper in a second, but the idea is you have your parameters you tune, and the model spits out a ton of data, all these fields, all these time points and everything. But what we actually are trying to fit to is not all the model outputs, but some specific aspects of the outputs, some specific things, some features of the data we choose to target. And that is what we're going to try to match while adjusting these parameters. Okay, so that's our task. Which data features and which parameters? So the parameters that they're tuning toward are listed in table 1. We have things like the entrainment rate of clouds in convection. We have the size of ice particles, which affects radiation. We have some parameters related to the boundary layer. Essentially, most of these, and not all, are related to the kind of in-place physics that happen at one point in the model. A few of them are more related to the dynamics that describe how things move around in the model. But by and large, is the parameterizations related to the in-place physics which we're tuning. Okay, so these are the parameters we're tuning. I think they look at either 7 or even 14 when they're trying to be more ambitious, though as we'll see, this doesn't always work out so well. And then what are they trying to match? Well, they have all these data features. So what are they're doing? They're running the model. They're starting with unperturbed parameters, standard parameters, and they're starting with a model state around December 1998. They're running it till February 2005 for about 6 years. And then they're using the first 2 years as kind of an equilibration period, a burn-in, where the change in the parameters will cause the model state to change. And then having done that, it's going to, we're going to then kind of get a different set of dynamics in the model that are consistent with the new parameters. So the first 2 years are discarded as the system state adjusts to the new parameters, and then they're taking the time period from 2000 to 2005. And then they're taking, it's about 5 years of data. And then what they're doing is they're taking a full 5-year average, either in the extratropical northern hemisphere or in the tropics. And I believe they also look at the southern hemisphere extratropical stuff, but then this turns out to be very correlated with the northern hemisphere, so they drop it at some point. So they're looking at these averages over 5 years, and averages of what? Land air temperature, land precipitation, mean sea level pressure, reflected shortwave radiation, what's coming off the Earth, outgoing long wave radiation, and the temperature at 500 hectopascals, as well as the humidity up there. So these are the fields they're looking at. They're looking at 5-year averages. They're not looking at monthly averages. They're not looking at specific spatial regions. So these are just very coarse, global, heavily spatially averaged measures of the model output. And then they're trying to adjust their 7 or 14 parameters to match these features of the model output. Okay, so then how do they do this? Ideally, you'd like to try optimization, which says we're going to look at these derivatives, right? Given these model outputs, so output I, which might be whatever, extratropical northern hemisphere, sea level pressure. And then you're going to look at its gradient or derivative with respect to one of the parameters, say the size of the ice particles in clouds. So if I look at the jth parameter, if I make an infinitesimal perturbation to it, what is the rate of change of the derivative, the gradient of the ith output that we've chosen to measure of the model? So the idea is you build up these sensitivities. How much does each output change with respect to a perturbation of each input? And then we're going to basically, that'll tell us which direction to perturb all the parameters in order to get a good match to our data. Okay, so there's several problems here. The number one biggest problem, I'd say, is that, we don't actually have a differentiable model, right? So if we have some function mapping inputs to outputs that we can take derivatives of, great. But what we have here is just a simulator code, which we can run for different parameters, but we don't have a way of taking gradients. We don't have what you'd call an adjoint in an easily accessible way. So how do they estimate these? They estimate these using finite differences. So instead of an infinitesimal perturbation, they take a finite perturbation and make a perturbation delta p of the parameters, and then they measure the slope, the rate of change of the output for each of these 5-year averages in these different regions of what we want to measure. Okay, so this allows us to estimate how much the outputs change with the inputs, not perhaps in an ideal way, because you have to guess how big of a perturbation you should make. If it's too small, then everything sort of gets lost in the noise and the numerical inaccuracies of the machine precision over all these computations, and you get a very noisy output. If you make it too big, then it's not really a gradient, it's really a finite step. So you'd like to have delta p not too big and not too small. They mentioned some references, notes it all and right about how to choose it. We're not going to go into that now. Once you've estimated these gradients, then you can make an adjustment. So you want to make an adjustment, little s, to your parameters based on your sensitivities J as well as C, which is a covariance, saying how much variability do we expect in what we're measuring. And they break this down into several sources. There's observation error, which they kind of look at from comparing different observational data sets to each other. This tells you how much parameters to expect. And then they also look at error arising from internal variability of the models. And then they estimate this by looking at different model runs from initial conditions at the default parameters. Okay. And so using this mathematical framework, they're able to make perturbations to the model parameters, and then they're able to adjust everything to get a better and better match to the averages over these features they've chosen, like land temperature, sea level pressure, humidity at 500 hectopascal, and so on. There's a lot more details which I'm not really going to go into, but they're all there in the paper if you want to check them out. Having figured out the update they're going to make, this little s here in this Gauss-Newton method, where they solve for the update, they then try to make the update, and if it's too big, they keep reducing it until they get the mismatch between the data and the prediction to go down. When they evaluate that mismatch, it's important to note that they're scaling the mismatch for each of the features they want to detect based on their estimates of observation error and internal variability, right? So if basically one of these things, say, land air temperature is not very predictable compared to, say, land precipitation, then they'll weight that less in quantifying the mismatch, and then it'll have less of an effect on how the parameters evolve. So I've explained a few concepts here. This is a good chance to chime in with a question. If anyone isn't so familiar with this kind of optimization, or if anyone wants to ask about a specific aspect of what they're doing, this is a great time. Otherwise, I will just carry on. So one thing that occurs to me as I think of this approach, where you have these parameters, you have these outputs, and you tweak them and observe, you make these adjustments, you have finite differences to estimate gradients, you follow the gradients to improve the predictions and reduce mismatch. You're really only interested in perturbations to your local parameters, right? So as your parameters get updated over and over again, you want to know, if I make an infinitesimal perturbation given my current parameters, how will the outputs change? But that means that all the old simulations, which are already now far from the current parameters, from the initial parameters and everything in between, right? As we evolve these parameters, we're going farther and farther away from our initial conditions, and that means our old simulations essentially become useless. So with these gradient-based optimizations, it's a little unfortunate that a lot of computation sort of gets wasted as we move forward. Okay, a question I have, and maybe if someone can answer this for me, because I really don't know the answer to this, is how exactly are these model runs initialized? So I looked in the methods, I looked at the references, at least one layer deep, I could not figure this out. I assume that they've run had CM3 or had AM3 in some cases with standard settings, and then in 1999, when they want to switch to their other parameters, they take the model state and that's their initialization. They change the parameters but keep the state. What I don't understand is, are they using the exact same initial state in every case? Are they using different initial states by perturbing them, or using different members of an ensemble? How does this work? I couldn't figure this out. If someone can explain it to me, I would love to know. But okay, they run these tuning experiments. They use the atmospheric only version of the Hadley model. They use a higher version, had a high resolution version, had AM3P. And then they also will look at some couple models at the end, but not during the tuning, I don't think. So if we look at figure 1, we have on the y-axis a cost function. This is basically the mismatch of all these different features they want to match, weighted by our estimates of internal variability and observations. So they have less weight if we expect them to be more variable. The black dashed line is the
mismatched observations for the default parameters, and then the other lines are basically our attempts to tune the model. These are different runs with different initial parameters, but I think all the same initial model state conditions. And you can see we do about as well, but not significantly better. They've got some kind of standard deviation error bars around the standard model performance. When they look at 14 parameters instead of 7, they're able to do a little bit better. And then they're able to do just a few runs at the high resolution because it's quite expensive. So it's not like a slam dunk, but they're able to show that it is possible to fit these parameters and maybe in some cases do slightly better than the defaults. One issue they mentioned here, and I think it's particularly an issue for this approach, similar approaches that use optimization that try to find a single best, hence the title of this episode, Best of All Possible Worlds, given our data, right? The best match to what we know, the best model of parameters that explain our observations of the world. An issue with that is this great word that I had to look up in the dictionary, equifinality. So equifinality refers to the concept that we have different model parameters which are going to exhibit the same final outputs in terms of all these 5-year means of these different fields in the tropics and northern hemisphere extratropics. So we're going to get the same results, either exactly or on average, with different parameters. Now, this may not be a big deal. You say, okay, fine, they're all equally good for predicting this past data, and we'll just choose whatever is best. We don't care if it's better by 0.001% or 10%. We'll just choose the best one. This, however, becomes a real problem when we actually want to use the results, presumably to make predictions for the future, because it's very well possible that many different parameter sets are going to match past data roughly equally well. They'll exhibit equifinality in the way they explain the past data, but they may have very different predictions for the future. They may have very different climate sensitivities, for example. They may have very different predictions for weather extremes. So if we can't tell them apart, given past data, we end up having considerable parameter uncertainty in our predictions of what's going to happen in the future. And in order to accurately incorporate that parameter uncertainty, we don't want to just settle on one set of parameters. We don't want to just have one best of all possible worlds. We want to have a range of possibilities, and that's going to motivate some of the papers that we're going to look at next. So then before moving on, let me once again take any questions we have regarding this paper, regarding the basic concepts. You can see here the parameter values before and after tuning. The black diamonds are the default parameters. You can see in some cases it really changes a bit. Oh yeah, before we move on, one more thing. Then in addition to just testing how well they're able to fit these 5-year average of the fields they were trying to fit, they then took the parameters after fitting and did coupled climate model simulations. And then they were able to look at just the basic phenomenology of what these models did. When we couple them to dynamic ocean models, as that they used, I believe, slab ocean models during tuning in order to save computation time. But when they do coupled models, then they're able to say, okay, do these results still make sense? And by and large, they sort of did make sense. I think a few of their models did no longer work so well when they coupled them to a dynamic ocean, as we can see here. Okay, but so we won't go too much more into that, but there's a lot more details if anyone wants to look. So there's a question from Johannes Tim. Yes, the question is, the cost of parameter tuning for high resolution are a problem in practice, and that is very true.
So some of these papers mention the idea of trying to find a way of translating between low and high resolution runs for the same model, with the hope you could use low resolution runs to tune high resolution ones. This is maybe a questionable idea, might work, it might not. Another idea, and this is what's going to come up in the next paper, I don't know how practical it is for modern climate models, but in this next paper we're going to look at, Williamson et al. 2013, they actually run a lot of climate models using this Weather at Home project. So Weather at Home is a really nice, nice idea. It's from climateprediction.net, and the basic idea is people donate their home computers to run climate model simulations, and they run a whole bunch of different projects. So here's the here's just a list of projects they're running right now. So we have, recent stuff is like they're modeling a specific drought. They're looking at stuff in Africa, causes of extreme heat in the Western U.S., something in East Asia, the early 19th, early 20th, late 19th century, the transition into the Anthropocene. So in all these projects, people are donating their home computers to essentially run these climate models. And for Williamson et al., what's happened is they've used so they actually ran 10,000 simulations. I think they didn't all finish in time for this paper, but they ran 10,000 different runs of HAD CM3. I guess it took on average of 30 days to do these runs, and not particularly long runs. I think they're just a few years each on people's home computers. And then they're able then to use this to do the parameter tuning. But as Johannes points out, this is still a lot of computation. I'd be curious if someone here is maybe more of an expert in kind of let's say the trade-offs of computing here in terms of the cost, in terms of power, in terms of money, in terms of time. In terms of what are the options if you want to do these big computations? You can get people to donate their computer time. That's an option. You can do cluster computing like we do at HZG, like our colleagues do at DKRZ. You can now do kind of this other solution where you kind of pay by the hour to rent huge numbers of processors from Amazon, Microsoft, or Google. You have your Amazon Elastic Compute servers, you have Microsoft Azure. I don't know. I think if you're doing tons of computation all the time, you're probably better off using your own cluster. If you're doing like occasionally a lot of computation, you might be better off buying from or renting from them. But all this stuff that I'm about to show, is it practical for a modern climate model? I don't know, and I'd love to hear if anyone. If anyone knows the ratio of, if I want to run these CMIP experiments with, say, Icon instead of with HAD CM3, how much more of a computational burden is it? I don't know. But okay, so what are they doing here? What are they doing in Williamson et al. 2013? The goal is the same, almost. We want to identify parameters of a Hadley Center model which are compatible with data. We choose some aspects of the data we want to match. We want to identify the parameters that match. But unlike Tett 2013, Williams in 2013, as well as some other similar papers we'll look at very briefly, they want to identify a whole range of possible parameters. So they're not trying to find the best of all possible worlds, but actually just a range of all possible worlds, which sort of are reasonably good given the data that we have and the aspects of it we have chosen to match. An important point they make very early into their paper is when we talk about parameter uncertainty, there's kind of two kinds of this, right? So let me just read the quote. One of the principal sources of this uncertainty is parametric uncertainty. This is the extent to which a single model can produce different projections, all consistent with current observations, through changing the values of the parameters in the model.
This includes the uncertainty present that we cannot, due to the fact that we cannot observe the model output for every, or indeed very many choices of the parameters of the model. So what are they saying here? They're saying, okay, if we could run 1 million simulations with all different parameters and look at the outputs, then we would still have some uncertainty because multiple parameter settings, multiple combinations of parameters would produce the same output. But it's actually even worse than that, because it's not like we can get this idealized case. Not only is there uncertainty in parameters given data for an unlimited computational budget, we also have a finite number of simulations which we can compute in practice. So there's this compounding of parameter uncertainty due to our limited computational budget. Okay, so with that in mind, they're using, whether at home, they're using these 10,000 simulations. And now, like in Tett 2013, they're defining a measure of how well a simulation matches the data. They're calling this, this is equation 4, I believe. They're calling this the implausibility measure. It's actually quite similar. I seem to have skipped it. It's essentially, yeah. So we have our observation Z. We have, given the expected output of our model, we want to look at how different is this from our observations, divided by the variability we'd expect, which can arise from several sources. It can arise, in this case, they consider observation error. They consider internal variability, saying if you run the model several times with similar initial conditions, you can get different results due to chaos, and just internal variability. And an additional source of variability they go to a lot of effort to estimate, which is basically how badly are the models themselves, the model classes, misspecified and unable to capture reality. So this is something I won't go into, but it's quite interesting on a mathematical as well as perhaps a philosophical level. So the idea is we have an implausibility measure. The mismatch between observations and predictions should not be too big relative to the variability. And we're going to set a threshold. In this case, it generally used 3 standard deviations. And we're going to rule out the parameter sets for which the predicted output is more than 3 standard deviations away from the observations. And an interesting thing about this approach is it's possible to rule out the entire parameter space and to conclude that there are no parameters for which this model can explain our observations. So this is a very nice thing that it can tell you, okay, go back to the drawing board. If you want to be within 3 standard deviations of your observations, forget it, you need to change your model. You need to go to higher resolution, you need to add more parameterizations, you need to do something different. Or maybe you need to look at if there's something wrong with your data. Okay, they, as in Tett 2013, they spin up the models after initialization. They run them, I believe, for an even shorter time. Let's see. So the spin up is quite. Says run up is spin up for 50 years at each of the 10,000 settings. So this is actually much more than Tett. And then they start doing a simulation of anthropogenic CO2 for 70 years. So they're actually simulating for quite a long time. This is an important point that some of the papers raise, in that if you want to look at parameters that have a rapid effect on the model state, say, for example, atmospheric parameters, you may only have to simulate for 2 years. Whereas if you're interested in, say, parameters describing what's happening in the ocean, which Williamson et al. Do, but Tett et al. 2013 do not do, then you may really have to simulate for longer, because it may take a long time for these ocean processes to equilibrate in your model, and so that you can actually see the effect of your parameter changes. Okay, so what is their overall strategy? It's very different from the optimization strategy. They have their 10,000 runs, where they've got
runs of the model with 10,000 different parameter settings, in which all of the parameters are randomly perturbed within their ranges. And then what they try to do is they fit this function called an emulator, which says, okay, for each output of the model that we're trying to predict, like this land-air temperature and so on, we'll get to the exact parameters and outputs we're covering here in a moment. For each one of these, we're going to try to model that function. This is basically classical machine learning, although they're not using neural networks. We're going to fit that function to our data. We're saying we want to predict the average output from the parameters. So the parameters here are x. We have some fixed functions. In this case, it turned out to be polynomials, second-order polynomials. So they'll look at linear functions plus products of the different parameters with each other plus parameters squared. And they'll take coefficients of that to build a polynomial. And they'll say that plus noise is equal to the expected value of the model output. So they're learning a mapping, a polynomial mapping. So consisting of first and second order terms from the parameters to the observables. Okay, so what are those in this case? And we'll get in a second to how they use this. But what are the parameters they're using? Yeah, this is description of the computation. 35,000 active hosts running for 28 days. It's a pretty monstrous computation. I was very lucky they were able to do it with volunteer computation. Okay, so the observational constraints, I believe we have them in a table. We have surface air temperature. We have the gradient of temperature over the hemisphere. We have and we have precipitation as well. We also have a change in temperature since pre-industrial time. So these are they're only doing 4 observational constraints. And you can see for each one, they've gone to some length to estimate the observational error by comparing 2 observation data sets to each other, and the overall variability by looking at the variability of ensemble members within a climate, I think a CMIP ensemble. These are the 4 constraints. And then what are the parameters they're tuning? They're tuning quite a lot in this case. I believe they're tuning actually a full 20 parameters. I believe they have them in a table. Yes. So here we go. We have all kinds of stuff: sea ice, clouds, convection, dynamics, sulfur cycle, ocean parameters. We have pretty broad ranges for each one of them. Okay. So this would not work using the Tett 2013 measure, right? Because every time we want to adjust our parameters in that case, we essentially have to do a perturbation of all 20 of these parameters. Then we have to do this over and over again. So this optimization approach really becomes computationally infeasible as we consider more and more of these parameters. So what do they do instead? Well, as I mentioned, they fit these functions, polynomial functions, which map from the input to the output. Now, unlike the model itself, where computing the output, that is these 4 constraints, the predicted value of these 4 observables, you know, the surface temperature, the gradient over time, gradient over space, and precipitation, predicting that for new parameters using one of these 10,000 model runs is really expensive. It requires someone to donate their computer to you for free for 28 days. But once you fit this function, to the extent that you trust this function, you can compute it instantly. It's now a polynomial. Instead of, you know, a climate model with 100,000 lines of Fortran code, this will now run in, you know, microseconds. So now, once we have this emulator, this proxy, this mapping, approximate mapping from our parameters to our outputs, once we fit that, we can now quickly identify all the regions of parameter space, which, according to our emulator, according to this approximation, are consistent with our observations. So this is essentially what they do. And they use it to explore the parameter space consistent with their observables. One interesting thing they do is, because they're now able to explore a large parameter space very quickly, because they trained this using free donated computation time. And once they have it, they only use 10,000 to train it, but once they've trained it, they're able to quickly calculate this for 1.5 million parameter sets. They're able to calculate their predicted outputs. So they actually devote 20% of their simulations to those outside of the classically approved ranges based on experts. And they show that some of these, normally non-probed or non-accepted parameter ranges are equally compatible with the data. They also, so another thing worth noting before we move on is if we look, say, section 3.2, they want to basically use these time and space average constraints because they don't want to fit too tightly to the individual fields in space and time, because they say this would require a lot more simulations probably to identify parameters that would be consistent with it. And even for the same parameters, it might be very dependent on the initial conditions, and you might need to do a large ensemble. So they're really arguing for this averaging. As a general point, this might or might not be worth doing. Another point that's worth noting is that, in our last episode, we covered Chris's paper where he filled in the missing values for this Hadkrut temperature data set. I can't remember if it was Hadkrut 3 or 4, but he really filled in a lot of these missing values. So they're actually using Hadkrut here for the surface air temperature. So perhaps, Chris, if they had your method, they could have had slightly more accurate constraints when tuning their models. Okay, so having fit this emulator function, this polynomial function that maps in an approximate way from input parameters to outputs, they can now quickly probe the whole parameter space and see which ones are within their 3 standard deviations of the observational data. Okay, and what happens when they do that? They get these beautiful figures. So let's start with the predicted outputs, right? So here we're looking at pairs of these observational constraints like surface air temperature and the gradient of the surface air temperature of the northern hemisphere. We can see, first of all, the distributions. We see, for one thing, they're very highly non-Gaussian, which sort of it questions the idea of optimizing in least squares or least absolute value as some of these papers do. But we see this distribution of the predicted outputs over our 10,000, now this is now, I believe, 1.5 million. This is actually still just the ensemble that was trained on this, so the 10,000 values, right? So we can see which of these are inside the constraints and which are out. But this is not for the full parameter space. It's only where we happen to generate our simulations. And you can see the model outputs, these pairs of model outputs and red lines of constraints. So when we're on the bottom left quadrant, then we're actually satisfying these constraints. So then here is where the real magic happens. Having fit the emulator, they now probe over the full parameter space, 1.5 million random samples, and use our emulator to quickly calculate the predicted output. And then it's not necessarily the true output, but it's a good approximation. They quantify how good an approximation in the supplementary material, if anyone wants to have a look. And now they're able to say, okay, what is our discrepancy with our observations across our parameter space? Now, this is a little tricky to read, so let me explain what we're looking at. We're looking here at 7 different parameters, right? And we'll start with the upper right here. So here we have the entrainment coefficient and CT. I'm not sure what CT is, but we have these 2 parameters, right? And we can see for gray or white, we're seeing a very good match. And then for red, we're seeing not such a good match. Which is the opposite way around. We filter out the points which do match, and then what's left, we look at the density of the points. And so the best match is right here in the red and orange. Okay, so how does this work? We started with 10,000 simulations. We fed our emulator to those. We then did 1.5 million pseudo simulations. And then we take all of them, that pass our criterion of matching the data on each of these 4 constraints with 1.5 standard deviations. We then project them to the 2-dimensional space because they're all 20-dimensional parameters. We project them to the 2-dimensional space just containing these 2 parameters. And in 2 dimensions, instead of 20, we can actually visualize them. So we see where they fall in this 2-dimensional parameter space. And we see they fall along this curve. What can one say here? We know from a lot of studies that the entrainment coefficient is very important to climate sensitivity because it affects how clouds form, and in particular, how they form with changes in temperature. So we know it's important. But what we see here is that, it's actually, we're getting a good match to the data for a wide range of entrainment coefficients. And it's only possible to rule out a value of the entrainment coefficient in combination with one of the other coefficients. So it's possible essentially to constrain the parameters collectively, but not really to constrain them individually. But okay, so what we're seeing is for each pair of parameters, the range in bright red where they can jointly lie and be consistent with the data according to our emulator. And they'll do some further tests later. On the right-hand side, it matches the color bar, but you can see there's very different scales for these different combinations. So if we look at these 2 parameters, we see a very sharp constraint. It really has to lie on this curve. If we look at these 2 parameters, it's not particularly good or bad anywhere. It's just kind of okay everywhere. And one has to keep in mind that when you look at one point on this graph, you're actually averaging or integrating over the other 18 dimensions of the parameter space. So this says if we look at averaged over all the other 18 parameters, how good is it to have this particular pair of parameters in this particular place? It's a little complicated. If I haven't explained this so well, please feel free to chime in, ask questions. But what we're essentially seeing here is a way of showing which regions of parameter space, when you look at pairs of parameters, are consistent with the data. We can see is these beautiful nonlinear, non-Gaussian regions that we've identified. And having identified, now we could actually do simulations within this region of what they call not yet ruled out space. And they call it not yet ruled out because, of course, we could look at other aspects of the data or do more simulations and update our emulator based on those. And this might cause us to change what we accept as a reasonable simulation parameters. Okay. And then as I mentioned, indeed, it is more difficult to constrain the ocean parameters, the atmospheric parameters, because they, may have to integrate for longer to do that. Okay. There's a lot more details, which I will leave to everyone if you want to dig into this more on your own. But one thing I do want to get onto is in figure 8, they actually use these results to make projections. So given the parameter sets that they identify using this procedure, they then run real simulations, not just not only emulators to predict model outputs for these 4 things we chose, but now they're going to take parameters which, based on this full analysis, are consistent with the data and do full simulations with these in coupled models. And now they're looking at something else. Specifically, they're looking at the Atlantic meridional overturning circulation and meridional heat transport. These are things that this whole procedure was not tuned to, but they find that compared to the overall plausible ranges of the parameters, after tuning, if you look at in blue, the not yet ruled out, the 1% best of these models, according to their procedure, they tend to show a larger prediction in the decrease of the AMOC and MHT, which of course could lead to considerable changes in European climate. So this was their particular scientific motivation. They find they're able to use this procedure to make predictions with parameter uncertainty. You can see that after rejecting a bunch of parameters using this procedure of history matching, they're able to have smaller error bars than they would otherwise. I will, again, this is a good time to chime in with a question, just to review very, very briefly the basic concept here. We have 10,000 simulations. We define an error metric saying how well they have to match the data before we reject them. We fit polynomials to match inputs to outputs based on 10,000 simulations. We use this to sample 1.5 million simulations with our emulator, our polynomial, and then this tells us which regions of parameter space might be consistent with our data. And so this is, again, addressing one way of trying to address Johannes's very important objection that you need a lot of computation. So another question in chat from Eduardo: why isn't figure 3 symmetric? Yeah, that's a good question. It actually is symmetric, but there's just different data scaling above and below the diagonal. So it's the same data. So if we look at this, it's a mirror image of this. But in the upper right, it's scaled so that they all have common units of the density of points in the in this 1.5 million parameter sets that after generating them and then throwing out, I believe, 40 or 50%, which are not predicted based on the emulator to satisfy the constraints, then we look at the density of the remaining points that pass the constraints. And they want to have the same units of density for everything in the upper right-hand side. In the lower left-hand side, each one of these boxes has its own unit so that you can see the fine features a little bit better, but it means they're no longer directly comparable to each other. So you can see the transition boundaries, but they're just much shallower for certain pairs of parameters than for others. What you see with the entrainment coefficient is that no matter what parameter you compare it to, there really is only a certain reasonable range. If you go too far above, high or low, then it's going to get very narrow. However, if you fix one of the other parameters, the reasonable range of the entrainment parameter can get much shorter. If you look at these two parameters here, you see they're kind of mutually constrained. Either one individually is not constrained at all, but mutually they have to be kind of in the upper left-hand side. Okay. I hope that explains the this kind of funny way of displaying things I did. All right, so I want to keep it short. I was very impressed with how Chris kept on a tight schedule last time. I have not been able to do that consistently at all. So I'm going to breeze through the remaining papers and try to save some time for discussion at the end. So the next one I want to get is, it came out roughly the same time, and it did roughly the same thing. This is Belprat, I don't know if I'm pronouncing that right, 2012. It did basically the same stuff as Williams in 2013. It again used, but it used this history matching approach of generating a big ensemble using a polynomial emulator. In this case, it only went to second order. I believe Williamson went to third order. But instead of doing a global general circulation model, a climate model, they did regional models. And this leads to a whole different set of questions. They use they look at different parameters. They tend to look at higher resolutions. They look at different constraints from the data. I won't go into the detail too much here. A couple things I want to point out is that when choosing their parameter sets, instead of just doing it randomly within the constraints using these Latin hypercube sampling, like where you just generate a whole bunch of spaced out points that cover your multi-dimensional parameter domain, they actually carefully designed their parameter sets so that they would be able to optimally estimate the quadratic terms and how interactions between different parameters influence the predicted outputs. So in figure 4, they describe how to design where to sample their parameter space in order to measure these interactions very nicely. They get these beautiful results similar to figure 3 of Williamson, where they look at regions of the density of accepted points. Instead of looking at density, but they're actually looking at predicted performance as a function of these parameters. It's a little bit different. And so then they're looking at contours of this in the parameter space. And they also explicitly, and you can see this in the supplementary material, but of Williamson as well, but they say, okay, we fit these emulators, which are super fast to run and allow us to do 1 million simulations instead of 10,000, and allow us to do it on their laptop instead of on 35,000 borrowed machines from volunteers. And you can see it's actually really good. They're predicting the 2-meter temperature, precipitation, and so on at really high correlations. They're doing a good job with these fits. So that's nice as well. And then finally, I want to look at Belprat 2016 very quickly. I'm going to say very little about this besides pointing everyone to this, but they basically ask, well, if we do this fitting procedure on 2 different regions, Europe and North America, and we compare the parameters, then how well do they actually match? And this it's basically, they find that they match in some ways and not others, but there really are some real differences, and this calls some of the conclusions. Maybe it raises some interesting questions that really ought to be addressed when comparing the different model parameters to each other. They're really not the same parameters are not always optimal in the different cases. But in many cases they are. Okay, so I won't go into that too much more. We can cover it more if people are interested. Finally, and this is where we get to the machine learning part, although arguably the polynomial fitting we've seen is machine learning already, is Lee et al. 2017. So again, as Marcel pointed out in the beginning, as we've seen, every one of these papers targets different aspects of the data. And they want to tune their parameters to match, whether it's 5-year average of land air temperature, whether it's warming trends, whether it's precipitation. These guys are really interested in targeting specific biases, in this case, in specific regions in the Hadley model. And I think they even look at specific months of the year. So you can really target this parameter tuning procedure depending on what you want your model to reproduce. And so what they do is basically the same approach we just saw in Belprat and Williamson, but here, instead of these relatively inflexible, poorly generalizing, hard to fit, easy to fit but hard to fit closely to your data polynomial models, they use an artificial neural network to predict, in this case, short and long wave radiation observables based on the parameters of their model. So they want to they want to basically match the radiation balance. And so they do simulations, again, using this Weather at Home, climateprediction.net distributed computing framework. And then they go through, they fit their emulator, now a neural network. They fit 17 parameters. Again, we can see all different aspects: dynamics, land surface, boundary layer, cloud, radiation is big, of course. But of course, you see any of these could affect the behavior of the model over the long term. They're using now a more recent, up-to-date version of the Weather at Home, which includes a more, I think, updated land surface model. They perturb those 17 parameters. They observe. They're trying to match basically certain biases in terms of certain months and certain regions. And so they feed their very simple 2-layer feed-forward artificial neural network. They use this to identify which regions of parameter space can match the data. They then generate a bunch of parameter sets from that, and then they do further filtering out using other techniques besides neural networks. They use kriging, which is a kind of interpolation, and there they actually target the biases, not only the radiative fluxes. They do several rounds of this. This is a common idea of, you do several iterative filtering of your procedures for your parameter space. You start with a full parameter space, you fit an emulator based on some simulations, you throw out a bunch of the parameter space, you do more simulations with the original expensive model in the reduced parameter space, you use that to fit a new emulator, and so on. And eventually you may converge to a relatively narrow set of parameter space. Here you can see the basically they're reflected shortwave from the surface and the outgoing long-range radiation from the upper atmosphere. And you can see their constraints are these red lines. They want to be between these two red lines. You can see the initial standard parameters, and then they have several phases of refinement to get inside here. Only the first phase uses the neural network that's in gray. They throw that out. They get the next phase in darker gray. They do kriging, and then they get the black. And so, having done this, they're able to use their emulator to actually look at, for example, average temperature cycles as a function of various parameters. So to see how to do kind of a sensitivity analysis for their model, which would be very difficult to do with just a simulator itself. Without an emulator, it would require a lot of computation. They do another validation. In their appendix, they measure how accurate their emulators are. You can see that here. They're not perfect, but they're pretty good depending on what they're trying to emulate. And this is all basically each observable as a function of, for example, the annual temperature cycle, long wave radiation, short wave radiation, various months of the year biases. And we're trying to predict this as a function of all 17 parameters. Okay, and so then they run the history matching. They are able then to look at biases in different months. They're able to look at, this is a really nice figure. I like this. It's a little complicated again. Sort of a scatter plot analog of Williamson figure 3 and Bell-Pratt, the analogous figure as well. You can see here's all their model inputs, so their simulations. Basically we have our all our different parameters, like the entrainment coefficient, mixing coefficients, land surface coefficients describing how fluxes depend on water saturation. Then here we have, basically it's a scatter plot comparing each one to the other. So we have a view of all the data, see how they spread across the ranges of these parameters, pretty uniform. But when we do those simulations, we can see here are the output distributions. So the December, January, February bias, long wave radiation output, short wave reflection of the surface. You can see here are the distributions. They're highly non-Gaussian. They're this nonlinear structure. I believe standard parameters are in red. And then they also compare every input variable to every output variable. You can see these nonlinear curves. Sometimes you have no interactions. Sometimes you have sort of complicated interactions of different shapes, weak correlations, strong correlations. This is just describing their simulations. So they fit it, they get their range of plausible parameter values using these methods, now combining these previous techniques of history matching with neural networks. And now they also do simulations with, okay, we fit this on regional models. Northwest US is where a lot of our biases come from. The model is global, but the observables we're fitting to are regional. And now we ask what happens across the rest of the globe, what happens to our zonal temperature profiles and precipitation profiles, what happens to the biases around the globe. They find in some places temperatures biases are getting better everywhere, even though they only tried to fit it in the Northwestern US. So you can see compared to standard parameters, biases are a lot less in the Northwestern US, but they actually are less in other places too. For example, in Central Asia, the bias is less. In some parts of Africa, it's less. In some parts of the Amazon, the bias is more in precipitation. That's a problem which they acknowledge. So they could have fit perhaps on both, but they chose not to. It's a generally open question. If you try to fit on a lot of different things, will you be able to? Or are the models simply not capable of doing that? Are you going to hit limitation of how well the models can fit the data? I think that's not clear from any of the studies. So this is it. We've seen how these different techniques work. We've seen how the data, and they use different data. We've seen how they either adjusted the parameters bit by bit to reach target, a single best of all possible worlds, or they used a surrogate function, an emulator, to quickly map between inputs, which are parameters, and outputs, which are observables, and then to identify the region of parameter space which matches the data. And how you can train this using simulations, but then quickly use it to explore the full parameter space. So that's all the material we wanted to cover. We're in just under an hour and a half, which I would count as a small victory. I have a lot of questions and comments, but I would much rather hear what everyone else has to say, what their opinions are, what wasn't clear, what was interesting, what else might be worth thinking about here. So you can ask, you can raise your hand, you can text in the Zoom chat or just chime in on Zoom, or you can write on the YouTube. I'm sort of missing the YouTube comments. I know there's 6 people watching on YouTube, so please make yourself heard. Yeah, Crystal.
So I think it's great, David. Thanks for all this wrap up. I just looked up what we did with the MPI-ESIM, so the Max Planck Institute model, the last time with the resolution step from LR to HR for low resolution to high resolution. And what they did was like many, but not long runs with the ECM, so just the atmosphere model. That took, that wasn't much. But then they needed to make a 2,000-year run to find equilibrium in the ocean.
Wow.
And if just put that into context with the 50-year runs of the paper you showed us to before, and then you actually the interesting thing about that is that they look at the Sverdrup in the AMOC you showed as well. And that's kind of if this is stable, then you can say your model is stable and can you use it to run forward. So I see the criticism a little bit like other colleagues. The runs are a little bit short, and this weather at home is great for short runs, which are, I don't know, seasonal predictions or that something like that could be great. But if you really need really long runs to find an answer,
yeah,
then I'm not sure if this is kind of the best thing. I just wanted to tell you that to put it a little bit into perspective here.
Yeah, I mean, I agree. It's totally impossible to do these approaches in that case. Yeah.
But I have a question to the last paper, actually. Did they talk about as well that you train in the recent climate, which is changing, and then you want to do maybe predictions or something like that, or projections? So kind of that you have trained, so you don't have an access to the future, basically. Do they say something like that?
I'm not sure I fully understand the question. Can you repeat that in a little more detail, maybe?
Sorry. So what I mean is that you train your parametrizations on the recent climate.
Yeah.
So like the last 6 years or something like that. What do you do when you make projections 100 years into the future? Are these emulators crashing then, or are they able to do that?
The emulators will not predict anything into the future. The emulators will only tell you which parameters you should choose. But then, so for example, going back to Williamson,
you have 10,000 simulations, which don't go into the future. You use this to train the emulator, right?
Mm-hmm.
Then with the emulator, you do 1.5 million simulations, virtual simulations, emulated simulations, to identify valid parameter space regions from which the predicted output matches the past data. Having done that, you can choose from this restricted parameter space new parameter sets, but to do future predictions, you would still, in my understanding, you would still have to do numerical runs.
Mm-hmm.
You wouldn't be able to use the emulator to actually make future predictions. It would just tell you it would allow you to choose parameter settings based on the past, which match past data, which you could then run into the future.
Okay, but so you still have the problem that you can't really.
Yeah.
If these parameters are changing in the future, then we have a problem, basically.
Yeah. Well, hopefully it's just physics, right? Hopefully then the physics doesn't change. But it's a reasonable thing. I want to propose you, Chris, a little thought experiment. I think it's not really an answer to these criticisms you're making, but I want to propose it anyway, right? So imagine we had a model which really is we had a really good model with good physics, which captures what's going on in the real world with good parameterizations. If you look at how these models are defined, all the actions of how these variables update themselves and each other, all the advection, all the in-place physics, it's all local in space and time. There's no long-range instant interactions. And so, in principle, everything that happens over your 200 or 2,000 years of ocean simulation is just a deterministic direct consequence of the microphysics, which are happening in a few grid cells over a few months. So in principle, if you can fit the correct microphysics, you should get the correct macrophysics. So maybe, just maybe in the right scenario, you could learn from shorter simulations in such a way that you get the microphysics just right, in that it could predict long-term simulations as well. Now, this is a big assumption, but maybe it's possible. What do you think?
Yeah, you can be right. That's possible. I was thinking about maybe that this learning algorithm is not just trained on the outside, but is learning through the run. So it's kind of an online dynamical model which could adjust itself to that procedure, and that could be also an option. But you're right. Yeah, but you're right. That could be also something that, and we could with perfect model approaches, you could do that actually, right? You can at least try to figure out if you're able to get the model range of the CMIP6 scenarios or something right? Yeah. So you can test things on a shorter scale to see if you could and put that into the future. And just put another aspect into the room, and everybody's welcome to join you. I see a hand from Edo, that's good. Because climate is changing in time and space. And probably we could learn in regions which are just shifting climate states. And that could be also something that these things are not totally changing and not all at once, but this is kind of a shifting paradigm on the globe. That could be also something which could help and kind of say this parameter tuning could work, and even with the machine learning in the background and the emulators. So I agree there are ways to do that. I just wanted to say that there are probably some reasons why it's not so easy. Let's to bring it up.
Edu, you had a question?
Yes, I have a question. Can you hear me?
Yeah.
Well, I have a question that has actually two, or they are related, two questions that are related, and also vaguely related to the question that Christopher just posed. And I'm a little bit worried about let's say, the possibility of overfitting. And then my first question would be, let's imagine that we have a climate model that is wrong, that is complicated but wrong. Would we be able, or would it be possible, after this tuning procedure, to detect that this model is wrong? Let's say it would be impossible really to tune the model towards itself.
I mean, certainly with the Williamson et al. Approach, with the history matching in general, basically all the approaches except the first one, if you set
okay, you have to choose which aspects of the data you want to match. And if it's, for example, these kind of climatologies, these kind of precipitation patterns, and so on, if you choose them, and then there's no way your model class can reproduce them, this should essentially rule out all of parameter space in principle. Now, it never actually happened in their experiments, no matter what they did. But in principle, this history matching can tell you that your model is inadequate to describe the data. It depends, of course, on your simulation budget, how good your emulator will be. It depends on a number of factors, but in principle, that's possible. But this question of overtuning, and this is something I've just pulled up the Hourdin review. They talk about overtuning as is concerned, basically that if your model can't capture the physics perfectly, if you try to match it too well, it may move parameters to unrealistic regimes in order to kind of compensate for its own structural errors or errors in other parameters. And furthermore, if you have a finite list, whether it's 400 or 400 features, you're not going to fit everything. No one, at least so far, has been able to fit a climate model based on all the observations we have of the whole Earth in history, right? So unless you're doing that, it may very well be that while getting a better fit to the metrics you've chosen, you're getting worse biases in other places. And yeah, this is absolutely a concern. The one thing you can do is test the model on something it wasn't tuned on, right? So if you tune it based on whatever land air temperature, maybe test it on some other completely different field like precipitation, or test it in a coupled model scenario, or test it in a different region. So these are kind of general principles of, okay, I want to test the model on something it wasn't fit for, but it's an open question. I don't know. I don't know if you have similar issues, Edu, in paleoclimate as well, right? Like when you must have a lot of parameters you have to tune, describing, for example, how your proxies relate to climate model variables. And these have to be fit somehow.
Yeah, there are similar questions, perhaps from not exactly the same questions, but similar. The issue of all fitting is always present when trying to reconstruct past climate. So it's also a relationship. For instance, to the issue that you may find different climate models that are able to replicate the past observation, but for the wrong reasons. That they perhaps after some statistical tuning, they replicate the sparse paleoclimate observations, but then otherwise they differ in regions where observations are not present. So that's telling you that there may be a problem there. I was wondering if perhaps the final, not the final proof, but actually a strong support of this approach would be if we could apply it to to many or to several climate models that are being used for climate projections presently. And we know that before tuning, so as the models as they are now, they differ in the projections. Actually, they differ quite a lot, even for the global mean temperature. We may find projected warming between, let's say, 2.5 degrees to 5 or 6 degrees in 2100. Then the question would be, if after tuning, this divergence in the projected warming, or in other words, the climate sensitivity, would be much reduced. In other words, after tuning, then we will really converge to the same answer, to the same projections in the future. Then that would be really a very strong support that this approach actually is working. But I'm not aware that has been done so far. That is related to the previous question by Christopher. If this tuned model tuned models have been then used to produce revised projections of future warming.
Yeah, I don't know the answer to that. There definitely were projections in, I believe in one of the Belprop papers, it did make projections. But whether these were actually tested, and certainly long-term ones, I don't think so.
Mm-hmm. Well, yeah, it was more than a comment than a question.
Yeah. I should say we focused, I think, on a relatively narrow. Not necessarily. We covered what we could. But there's definitely other aspects of climate model tuning we didn't cover. We didn't cover probabilistic methods, which instead of just ruling parameter regions in or out, they assign them probabilities. We also didn't cover this whole body of work where people look at trying to tune the physics in individual columns, these single column models, while using forcings from a previous run and maybe some observational statistics on the local level. So there, maybe the computational problems are less, but the conceptual problems are more. Yeah, I think, like, in terms of overtuning, it's in machine learning in general, you can just use some held out data and say, okay, am I overfitting? I'm going to use validation data to tell me when I'm overfitting my data. But this is a more subtle problem in that it's really the model class itself, which isn't quite right. One might be able to just include more and more observations, which maybe are finer in space and time or more interesting, to constrain the parameters better and better, and then see, do they fit at all, or with this model, and if so, maybe we can constrain the parameters a lot better, and we'll have enough constraints that it won't be possible to overtune on all of them at once. But of course, to fit more constraints means you need emulators with more output, so you'll probably need more simulation data. So you're paying a price in terms of computation. So there's probably no easy answer. I want to make one comment. I think probably this has occurred to you, Marcel, as well. Is that looking at this literature, which I found extremely interesting to go over. I really enjoy preparing for this seminar. There's a lot of replicated creative work between this and the more pure statistics literature, which is now also more influenced by ML. But we talk about terms there like approximate Bayesian computation, versus here it would be ensemble filtering. Posterior inference versus uncertainty quantification, history matching and likelihood-free inference, synthetic likelihood, regression adjustment. We talk about equifinality in climate science and earth science, and they talk about parameter sloppiness in statistics. And generative modeling. So there's a lot of cases, I think, where the same concepts exist, or very similar concepts exist under different names in these different literatures. And I think it would be very worthwhile at some point to write a review, kind of comparing and uniting these terminologies and saying to the statisticians, hey, there are all these interesting problems and data sets to work on, and saying to the earth scientists, well, actually, there's a lot of code and a lot of math and a lot of papers available for you. People have been working on some of these techniques, in some cases, decades before they appeared under different names in the climate parameter tuning literature. So there's a lot of points of connection there. Any other questions? Anyone want to just chime in? I'm still hoping YouTube people, please write something in the chat. Some anonymous comment that can't be traced back to you. Okay, we have any other comments or questions? And I think we'll probably wrap up. Hour and 45 total is not too bad. All right, so thanks to everyone who participated. I really enjoyed this one a lot. We're always up for more suggestions for future seminars of short presentations, or if someone wants to take over and do the whole thing. There's a lot of interesting topics we would like to get into. You know, we covered parameter tuning today, the kind of the converse, or the kind of the companion kind of tuning that one might do, or the companion kind of inverse problem one solves is data assimilation. So it'd be great maybe to do a future seminar on the methods of data assimilation of 40var and the ensemble Kalman filter, and what machine learning might have to offer there. Anyway, just a thought. We really encourage suggestions. Yeah, thanks for everyone for participating.